Hello friends, welcome again to the tetrahedron chemistry classes. So today is Janmashtami. So a very happy Krishna Janmashtami to all of you. And in today's class I am going to discuss the CSIR net spectroscopic previous year problems. And today we will discuss the 2019 December problems. In the last lecture I have discussed the June 2019 problems, and in this lecture I will cover 7 problems, right? And so far in all the spectroscopic previous year questions right from the 2011, I think this December 2019 is the most easiest one, right? Because the problems are not that difficult. So straight away we will go to the questions, right? You can read what is my first question. The correct match of the 13C chemical shift values in delta ppm for pyridine is. So it's a heterocyclic compound, aromatic heterocyclic compound, pyridine, right? And in this pyridine you will have
दोस्तों, मैंने एक ये नया चैनल जो है एक डेली व्लॉगिंग का स्टार्ट किया है, जिसको देवलोग माई व्लॉग के नाम से जानते हैं। आप मुझे सपोर्ट करिए, जैसे आपने मेरा चैनल टेट्राहेड्रॉन केमिस्ट्री क्लासेस सपोर्ट किया है, वैसे इसे भी सपोर्ट करिए। प्लीज़ चैनल को सब्सक्राइब करिए, इसको शेयर भी करिए सब लोगों से। थैंक यू वेरी मच।
2, 3, 4, 5, 6. See, 2, 3, 4, 5, 6. That means total 5 carbons are there. But as you know, this molecule is having the plane of symmetry. Okay, guys, this molecule is having the plane of symmetry from somewhere here. Okay, which makes this carbon and this carbon equivalent. So basically, if you see the carbon NMR spectrum for such molecule, you will find only 3 peaks. Okay, and you have to tell the chemical shift of 2, 3, and 4th carbon atom in this. And to solve this kind of problem, what you will do, you will draw the resonance structure for the molecule. So how we can draw the structure, we can very easily see what can happen in that case. This electron pair which is here actually, right, this can come onto this nitrogen atom, and when it comes onto the nitrogen atom, you can make the another structure, and that structure would look like this. I'll try to make quickly, right? This is nitrogen, and this nitrogen is having this lone pair, and this carbon now would be positively charged, and this, and after that this would come here, the pi bond, and then you will make this structure, okay, and a positive over there, and of course the nitrogen is here. Okay, so you will draw these 3 structures. I hope it is clear to you. Now you can see here in that case what you are observing, this carbon, which is carbon number 2, it is electron deficient. That means it is de-shielded. Carbon number 4, it is also having the positive charge here, so it is also de-shielded. In the 2 resonance structure we can see this position number 2 and position number 4, they are the de-shielded protons, de-shielded carbon, so their chemical shift would be very high. Please remember, for carbon 2 and 4, chemical shift would be high. Chemical shift is high. What it means? It means that your carbon number 3 will have the lowest chemical shift value, because it is shielded proton. Electrons are there to shield the carbon actually, not protons, right? Carbon. So this is actually, I can write here, shielded. And when it is shielded, it will have lowest ppm value. So we will check in the options where this carbon number 3 is having the lowest value. So here you see 136, 124 and 150. The lowest value is 124 for C3. So this A could be your answer. But in that case C3 is 150, so B cannot be your answer. What you can do, you can very easily remove this option B from here. Now if you go further in the next, you see C3 is having 124, that means it can be your answer. A or C, anyone could be your answer. But if you go here for C3, it is 136. 136 is actually higher than this 124, so this D also cannot be your answer. So what you can do, you can remove this T also. Now you have to select between A and see which one is correct. Now the important thing is that both are equally electron deficient, this carbon 2 as well as carbon 4. But this nitrogen which is present here, nitrogen is electron withdrawing group. When nitrogen is electron withdrawing group, it will suck electron density towards itself inductively more effectively from carbon 2, as this carbon 2 is near to the nitrogen atom. But this carbon 4 is actually far away from this nitrogen atom, so this minus I effect would be less on this carbon number 4, right? While this minus I effect would be very high on this carbon 2, so that means it is very highly electron deficient. This carbon 2 is very highly electron deficient, so carbon 2 should have or not should, it must have, so carbon 2 will have the highest chemical shift, right? Highest ppm value. So we will check the options. Here you see carbon 2 is having 136, but 150. Option C is saying that C2 is actually 150, which is the highest value of in the ppm, and it indicates that it is highly deshielded. Okay, while C4 is not that highly deshielded, while C3 is very shielded. So that means your option C is the correct answer. You can discard this also, and then you can mark option C as the correct. So this is the very easy question, but you have to apply some concept, general organic chemistry as well as the chemical shift. Now moving to the next problem, what it says that, okay, my next problem say from your inorganic spectroscopy, but I am interested in the phosphorus NMR spectroscopy. That's why I always took the problem, or I generally take the problem from the phosphorus NMR spectroscopy. And here what the question says, for the complex shown here, this is the complex, this is the iridium complex. In the center you are having the iridium, right? In non-fluxional state, the expected phosphorus NMR resonance is R, and where the value of I, right, that is the quantum number, is half like proton for the phosphorus also. And I already told you, whenever you find this small bracket and inside this small bracket certain nuclei is there, that means this nuclei is decoupled. That means this proton will not affect the spectrum of the phosphorus. And more importantly, this is non-fluxional state. That means this molecule is quite rigid, and whatever the stereochemistry is there, it will be fixed, right? Because it is non-fluxional. So when it is non-fluxional, so what you can do, you can mark the different kinds of the phosphorus. So this P is the phosphorus, PH is the phenyl, right? Again, PH is the phenyl, P is the phosphorus, PH is the phenyl. So we have nothing to do with the pH. We'll check the phosphorus only. So here you can see this phosphorus, right? This above phosphorus is actually what? It is in the environment of this carbonyl, okay? While this phosphorus is in the environment of this CO. So here you see phenyl phosphine type things is there, right? And for this phosphorus your carbonyl is there. That means the environment of these two phosphorus is different. That means these two phosphorus are of different kind. When they are of the different kind, what I can do, I can mark this as phosphorus 1, and I can mark this as phosphorus 2. And when you calculate the multiplicity, right, so I can write, sorry, I can change the color here, multiplicity for phosphorus type 1, right? So I can write for P1 formula, you know what, 2Ni plus 1, where 2 is the constant, N is the number of the phosphorus atom, which is 1, and quantum number I is half, that is plus 1. Now these two gets cancelled and you will get a 2. That means you are getting a doublet for this one, okay? You are getting the doublet. So when you are getting the doublet, that means this A cannot be your answer, okay? So you can immediately discard this option A. Now go for the phosphorus 2. What I can do, I can calculate for phosphorus 2 multiplicity P2, and formula is what, 2Ni plus 1, and again you see 2, number of the two types of the phosphorus is 1 only, I is the half plus 1, that is 2, and again you are getting the doublet. So in the phosphorus NMR spectrum you will get the two doublet. One doublet is this one and another doublet is this one. the answer is the 2 doublets you are getting. When you are getting the 2 doublets, right, it simply means your option D is the correct one. So option D here is the correct answer. This is how you can solve the problem. It's a very easy problem, nothing to worry about that, right? Now moving to the next problem, what it says. Yes, this problem okay, this problem is quite a straightforward problem. You see, the frequency of the OH stretching occurs at around 3600 centimeter inverse. The OD stretching frequency in centimeter would occur at which value, whether it is 3000, 2600, 1800 or 900, where D is the deuterium, right? However, this deuterium can affect the bond strength, but it is not given in the question that it is affecting the bond strength. So we can easily apply the Hooke's law, right? So what is see, however, you can, if you know the short tricks and you have studied your IR spectroscopy in pretty much detail, physical IR spectroscopy, then it would be hardly take say 1 minute to solve this problem, okay? But for the beginners also, because see, the students who are watching the video for the first time and they are learning, they are start learning actually spectroscopic techniques. So for those students also I am going to take the problem in the detail, right? So for this we will apply the Hooke's law. And what the Hooke's law say, stretching frequency, that is nu bar, that would be equals to 1 upon 2 pi c square root of k by mu. And you know, this one is this part is constant, 2 pi 1 and c, this is the constant value, and k is again in that case the same in both the cases, not constant, but in the question it is not given, so you can take this k also constant, right? And this mu is the reduced mass. So for the reduced mass you are having the formula mu equals to m1 into m2 divided by m1 plus m2. That means if you have the diatomic molecule, okay, or diatomic species, so in that case you will multiply the atomic weight of both the atoms, and then you will add and then divide, you will get the value of the mu, right? And since you are having the two species, so what I can do, I can quickly write the expression. Say this is for OH, so definitely here this would be your mu OH, okay? So this is the equation number 1. On the same note, you can write the equation number 2, mu OD, and that is equals to 1 upon 2 pi c square root of k, that is force constant, divided by mu d. Say this is the equation number 2 from 1 and 2. That means what you will do, you will take the equation 1 and you will divide that equation with the equation 2, okay? And when you do that, then you will have what? Mu bar OH divided by mu bar OD. I can write OD here, and then here what you can do, you can write 1 upon 2 pi c square root of k by mu OH, and then divided by, you can write 1 upon 2 pi c square root of k divided by mu OD, right? So what you can do, you can cancel these and as well as this k, okay? And finally what you left with, since you know this is in the denominator, so this will go up, right? This is in the inverse of the denominator, this will go up, and this is already in the denominator, this will come down, okay? And your expression would be like that, mu OD divided by mu OH, right? So finally you have you come here actually, right? But if you know this relation, that means this mu OH actually, or this vibrational frequency, is inversely proportional to the reduced mass, then you can straightforward come to the conclusion that the expression would be like that, okay? So now you will put the value, right? So say this is the equation number 3. Say this is the equation number 3. So we'll put the values, right? You know this mu bar OH is 3600 centimeter inverse. It is given, guys. It is given in the question. This value, right? It is given in the question, it is approximately 3600 cm. Okay, and then you have to calculate what? Nu bar OD, this you have to calculate. And then you can go for the reduced mass. So how you can go for the reduced mass? It is again quite easy. Okay, so I already given you the formula for the reduced mass. So first of all, I am going for the say this mu OD, where deuterium is atomic weight is 2 and oxygen is 16, right? So what I'll do, I'll write 16 multiplied by 2 divided by 16 plus 2, okay, and then divided by your this value. Oxygen is 16, hydrogen is 1, that is protium. So you can write here 16 into 1 divided by 16 plus 1, and when you solve this value, then it will come 17 by 9. Okay, and from here you can calculate your mu bar. So it is just like that. I am writing here 3600 centimeter inverse divided by mu bar OD, and this will come near about 1.374, and if you solve this value, then your mu OD will come 2620 centimeter inverse, and you know this value 2620 is pretty close to the 2600. Okay, see, in the spectroscopy it is quite difficult to get the exact values. Okay, so this 2620 centimeter inverse is more close to the B. So option B you can mark as the correct answer in that case, right? So I can mark it as correct option. Now moving to the next problem, what it says. So your next problem, in the IR spectrum recorded a neat compound shows a strong band, strong and broad band at 3300 centimeter inverse. The band becomes sharper and shift to the 3600 centimeter inverse when the spectrum is recorded in the carbon tetrachloride. So out of these four options, where OH group is which is involved in the hydrogen bonding, or OH group which is involved in the intermolecular hydrogen bonding, right, and a terminal alkyne group, or the OH present in the severely sterically hindered environment, right? So out of these four options you have to select the correct answer, right? Correct option you have to select. Now for this you should know the effect of your hydrogen bonding on the IR stretching frequency. Okay, you should know this thing, right? So what is happening in that case? First of all, you need to understand the spectrum, right? Say if I am drawing the IR spectrum like that. Okay, so here I can write here nu bar values which are going to increase, and here I am writing percentage. Okay, so what can happen if it is saying that it is a very strong and the broad band? So it is initially, right, and this is for neat compound. Please remember, this is for neat, that means pure compound. Okay, please remember this thing. Now what can happen when we add some inert solvent to it, right? When non-polars, we add the non-polar solvent to it. Say for example, I have added carbon tetrachloride. Not for example, it is given in the question. Okay, carbon tetrachloride. So what will happen when you add the carbon tetrachloride? Okay, so initially that broad band due to the OH, this band is actually due to the hydrogen bonding, intermolecular hydrogen bonding. Intermolecular H bond. Okay, please remember, broad strong band around 3300 centimeter inverse is due to your hydrogen bonded OH group. So it is centered around 3300 centimeter inverse. Please remember. Okay, when you add this one and you dilute this sample, so the moment you dilute this sample, so your spectrum would look like that. Okay, say for example, now it will shift just like that. It will become sharper and it will concentrate somewhere around at 3600 centimeter inverse. Because what happens when we add the non-polar solvent to it, the extent of the intermolecular hydrogen bonding actually decreases. When the hydrogen bonding decreases, this broad band actually contracts and becomes very sharp, right? However, it is that strong right now again, but it becomes very, very sharp. So the correct option, it is looking at the decreasing intermolecular hydrogen bonding. And this option B, OH group, which is involved in the hydrogen bonding initially, now get actually this hydrogen bonding breaks due to the addition of this solvent. So option B in that case is looking the correct answer. So what you can do, you can mark option B as the correct answer. Okay, this is very simple. Now moving to the next problem. See, here you see what it says, that the terminal alkyne group. See, terminal alkyne group does not having this kind of the effect because it is not involved in the hydrogen bonding. Okay, and when it is having the sterically hindered environment, it is again the something different kind of thing. So it's straightforward. You can conclude that okay, intermolecular hydrogen bonding is there. Okay, so and for intramolecular hydrogen bonding, there is no effect of addition of this CaCCl4. Now moving to the next problem, what it's.
दोस्तों, मैंने एक ये नया चैनल जो है एक डेली व्लॉगिंग का स्टार्ट किया है, जिसको देवलोग माई व्लॉग के नाम से जानते हैं। आप मुझे सपोर्ट करिए, जैसे आपने मेरा चैनल टेट्राहेड्रॉन केमिस्ट्री क्लासेस सपोर्ट किया है, वैसे इसे भी सपोर्ट करिए। प्लीज़ चैनल को सब्सक्राइब करिए, इसको शेयर भी करिए सब लोगों से। थैंक यू वेरी मच।
This problem you see again a very straightforward. What I'll say, this problem is very straightforward and the easy problem. So there is no need to worry about this problem also. This is very simple problem. And what the problem says, you see the structure of the compound, right? These four compounds are given, and out of these four compounds, which one will display the following spectral data? And here you have been given 1690 centimeter inverse in the IR. And scanning is not very good. It should be 1100 centimeter inverse. These values are given here, and then you come then you can go here for proton NMR spectrum. You see doublet at 6.9 and another doublet at 7.9. That means two doublets. Again and again I am telling you this thing, and for the last 10 days, or sorry, for the last 5 days I am telling you this thing. Every time in the net examination they are asking the problem from the substituted aromatics, right? And all the time they are giving the two doublets, which means para di substitution. When you have the two doublets, please remember this thing. When you have the two doublets, that means you are having the para di substitution. Okay, when you are having the para di substitution, that means this D cannot be your answer. Okay, however, it is actually matching the condition of the proton NMR spectrum, but it is not matching that two doublet situation, right? So this is because this is not the para one. So this is ortho isomer. So what you can do, you can discard this off. While other three options, guys, you can see this is your para isomer. This is also para isomer. This is also para isomer, right? And so anyone could be correct. But again, the very simple thing which is given in the question itself, you can check your IR spectrum. So in the IR spectrum, it is saying that you are getting the peak at 1690, band at 1690 centimeter inverse. And please remember, below 1700, whenever you are having this band and your compound is actually having the carbonyl group, so it is due to the ketone. It is due to the ketone. If it was ester, right? If it was suppose it is ester, then it will have the value of 1725 centimeter inverse. Okay, so now you can check here. This is your ester, but IR is not supporting this ester, so you can discard this option also. And then you can come here. This is again ester, okay, but IR is not supporting this ester, so again you can discard this also. So what you left with the option C. That means option C is the correct answer in that case. Okay, and if you want, then you can go further. See what you can check here. 197. Please remember around 200 in 13C NMR. Please remember in 13C NMR, whenever you are having the value somewhere around 200 ppm, it is simply the ketonic group, right? It is simply the ketonic group. That means carbon NMR is also suggesting the ketone present. However, this 1100 centimeter 100 inverse is nothing, but it is the carbon single bond oxygen, right? Say this is carbon, this is single bond oxygen. So if you want, then you can characterize it fully also. How we can characterize fully? This is CH3. I can write CH3 here, and this is also CH3, right? But this you can check here. this carbonyl group is electron withdrawing, as well as this oxygen is also electron withdrawing for this methyl group, but this carbonyl group is not that electronegative than oxygen, right? So the oxygen is more electronegative, so it will actually de-shield this methyl protons, these methyl protons. This carbonyl will de-shield these methyl protons, but not to that extent that would be done by the oxygen here actually. Okay, so this should be downfield, but this should be farther downfield. So if you check the spectrum, it will give you the 3 proton singlet, and this will also give you the 3 proton singlet, but this will have the downfield shift. You can check here, singlet at 3.8. so this 3.8 is corresponding to this one. Okay, so you can write 3.8 here, and another singlet at 2.8 you can write here, and this is what your 197 ppm in the carbon NMR spectrum, as well as your 1690 centimeter inverse for this one. Okay, this is quite easy, guys, you can see, and this you can consider as 1100 centimeter inverse, or not this one, you can go for this one. Okay, so and what you left with the 2 doublets. So again you see here, this carbonyl is electron withdrawing, while this oxygen is actually electron donating. Okay, electrons are coming here, that means these hydrogens are shielded hydrogens. Okay, these hydrogens are shielded, and say this is H1 or H1 type of the hydrogen, and this is hydrogen H2 and H2, these are the de-shielded one. So for H2 hydrogen, H type 2 hydrogen, you will get a 2 proton doublet, which would be downfield, right? Downfield means somewhere around 7.8. And for H1 kind of the hydrogen, you will get 2 proton doublet, and that would be upfield, that is 6.9. That means, so this is how you can explain this problem, but again it is a very easy and a very simple problem. Now moving to the next problem, what it says that
दोस्तों, मैंने एक ये नया चैनल जो है एक डेली व्लॉगिंग का स्टार्ट किया है, जिसको देवलोग माई व्लॉग के नाम से जानते हैं। आप मुझे सपोर्ट करिए, जैसे आपने मेरा चैनल टेट्राहेड्रॉन केमिस्ट्री क्लासेस सपोर्ट किया है, वैसे इसे भी सपोर्ट करिए। प्लीज़ चैनल को सब्सक्राइब करिए, इसको शेयर भी करिए सब लोगों से। थैंक यू वेरी मच।
Okay, so because I forgot to scan that particular problems, I have written over there. In the trans 1,2-dichloroethylene, the IR inactive mode is, you have given 4 options. Out of these 4 options, you have to check which one is the IR active, which one is the IR inactive. So for this, what I can do, I can quickly draw the different frequencies or different structures. Okay, say this is H, this is H, this is Cl, this is Cl. Okay, and first say I am explaining a symmetrical stretch. CCl, symmetrical stretch I am going to explain. So when the symmetrical stretching would occur, what will happen? Both will go in the same direction. So this is going in that direction, this is going in that direction. Okay, and when these two are actually, these are the symmetrical stretch. Okay, so what will happen? Whatever the length would increase here, it would be counterbalanced by the length here. So in that case, your distance is not changing. That means dipole moment will not change. And you know the condition for the IR active molecule is that there must be the change in the dipole moment during the vibrations. Okay, but this is the symmetric vibration, no change in the dipole moment. So this is IR inactive. This is IR inactive mode. Okay, and when this is IR inactive mode, okay, this first one itself is actually the correct one. But if you want, then you can go further also. How? You see, this is say carbon, double bond carbon, this is my hydrogen, this is my chlorine again, this is my chlorine again. Draw trans structure already given in this question. Okay, and when it is your asymmetrical stretch, so what will happen? this will go in that direction, and this will also come in that direction. Okay, and you know these are the vectors. Dipole moment sign, it should be here actually. Okay, so when these two vectors are going in the same direction, so they will add up, and when they will add up, that means the distance will increase, this bond distance will increase, and you know the mu is equals to mu is directly proportional to the bond distance. That means in that case your dipole moment will change. Why dipole moment will change? That means it would be your IR active. So this is your IR active mode. So I can write active. And then you can go for the CH asymmetrical stretch. So like I have explained this for CCL. Similarly, you can explain for the CCH. If it is symmetrical one like that, say it is coming like that, asymmetric. It is showing asymmetric. Okay, it is again showing the asymmetric. It will come here. So both will come in the same direction. Okay, that means the dipole moment will change. So this mode would be IR active. This mode will also be IR active. Okay, so this is also active, right? And then the last one is your carbon, double bond carbon. This is hydrogen here, this is hydrogen here, and this is chlorine here, and this is chlorine here. Last one is it is saying that in phase OOP CCl bond. OOP is out of plane bending, right? Out of plane bend, it is saying. So that means, you know, in the stretching your bond length increases, and in the bending your bond angle changes, right? And when bond angle changes, this is plus and this is also plus. So what these two plus are indicating, this is coming out of the plane, this bond is coming out of the plane, as well as this bond is also coming out of the plane. Okay, so both are actually in phase. In phase, that means it will come up and this will also come up, right? Or you can put negative here, it can go down or it can go down. So when this will happen again, so both will come closer, right? Due to this, see, this will come here, this will come up, this will also come up, both will come closer. In that case, again the dipole moment would be dipole moment would change. So this would also be active. So in all the cases, you see this is active, this is also active, and this is also active. But the first one is the inactive mode, which the question is asking. Okay, now moving to the next problem, what it says. Okay guys, so this is my last problem, and what it says that the compound that shows the peak in the EIMS spectrum at M/Z value 121, 105, 177 and 44. So this problem actually I have solved in my mass spectrometry lecture. Okay, when I have explained the fragmentation pattern in the amides. So if you want, then you can search in the YouTube bar, right? Mass fragmentation pattern for amides by tetrahedron chemistry classes, then you will get the result. Apart along with this problem, you will get another thing also. Okay, so how we can solve this problem? Again, it's a very easy, very straightforward problem. First of all, you need to understand all these compounds are having the molecular ion, right? If they are aromatic, they are aromatic, not if, but since they are aromatic, they will produce the molecular ion, and it will have the M/Z value of 121 for all 120. And if you check the question, it is asking first peak as 120, first peak at 121, and next is the 105. So only this much we need to do. So what you will write? You will write the 121 here, and you will subtract 105 from here, and this will give you 6 and 1, that means 16. So that means neutral loss of 16, neutral loss of 16 AMU. How we can do that? The only way to do this, what? NH2. That means we have to remove the NH2 from there. So you can see this is species, right? This is CH3, this is CH3, this is N, right? And this is phenyl group. So this can never actually release this neutral NH2 group. So this C cannot be your answer. You can straightforward discard this C. Okay, you can straightforward discard. And then coming here, actually you see this is NH, this is amide linkage basically, and this hydrogen is this first, this hydrogen will go, right? So again, it is not looking very feasible to combine that NH with the H to remove this NH2. So this D is not a this D is again not a very good option. So you can discard this D also. Okay. Now you left with the two options. Option 1, this CHO and NH2, and second is NH2 and this one. Okay. But again, you see, if you remove, say for example, if you remove this NH2 from here and as a neutral species, so this actually the species which will form here as the cation, actually this not be a very stable cation. So this is not feasible. See, this NH2 we cannot remove from here, right? So this again you can discard. But in that case, you see, you can very easily remove this NH2 from here to get the next peak at 105. So option B in that case is looking correct answer. Okay. And see why I am not completing this problem, because this problem I have in the pretty much detail solved in my lecture of mass spectrometry. So it is up to you. If you want to learn those things, you can search in the YouTube bar, search bar of the YouTube, mass spectrometry by tetrahedron chemistry classes, then you will find the playlist there. Okay. So these are the problems, very easy problems. So we are stopping here, right? And in the next class, I'll cover the 2019 November questions, where see the questions which have been asked in the northeast area. I'll try to cover all of them. Okay. So but if you are new here and watching video for the first time, so it's my request, please subscribe the tetrahedron chemistry classes. Do share with your friends also. Okay. And don't forget to like the video. So that's it for today. Thank you very much.